In this video, I'm going to go through the OCR Chemistry A level. This is paper 3, Unified Chemistry, it's called, and this is the June 2018 paper. Okay, so I've pasted in this periodic table here to answer the first question. Okay, question refers to the elements in the first 3 periods. Okay, so helium to argon in the periodic table, that's what we've got there. Select an element that fits each of the following descriptions. An element that forms a 1- ion with the same electronic configuration as helium. Well, right, 1- is it's going to be right. So it's going to have a an electronic configuration of helium, which is just 2 electrons in the first shell, and it's going to have an extra electron. So that's going to be the hydride ion, H-. That will have the same electronic configuration as helium. Okay. The element with the highest first ionization energy. Well, that is helium. Okay. Helium has the highest first ionization energy of any element in the periodic table. That's because the electron is being removed from 1s, which is very close to the nucleus, and there's no shielding. Well, hydrogen, you might say, has also got that, but helium has got a bigger nuclear charge than hydrogen. It's got 2 protons, hydrogen's only got 1. So helium's is the highest first ionization energy in the periodic table, not from helium to argon, hydrogen to argon, but what this question is asking. Okay, the element in period 3 which has successive ionization energy is shown below. Right, so we can see here we've got that, and then we've got that, then we've got a really big jump. We've got a big jump there. So that suggests that the first 2 electrons are in one quantum shell and the third is from the next quantum shell. So we've got to say 2 electrons in the outer shell of that element. So it's obviously got to be in group 2. And it's in period 3, which is this one. So which element is group 2? It's magnesium. You look for the big jump, and that's when the third electron must be coming from, in this case, this electron is coming from 3s. That's coming from 3s. And then the third one is coming from 2p. So that's from a new quantum shell, much closer to the nucleus and less shielding. Okay, done the periodic table again there to answer more questions. The element which forms a compound with fluorine that has octahedral molecules. Right, so octahedral, it has got to be forming 6 bonds. So, and it's molecules, so it's got to be covalent, so it's none of the metals. Well, which element can form 6 bonds? It's got to be in group 6. It's not oxygen, it's sulfur. Now, oxygen can only form 2 bonds, even though it's got 6 electrons. It's not allowed to have more than 8 in its outer shell. Sulfur can, because that's in period 3. Okay, so there's room for more than 8 electrons. An element which reacts with water to form an acidic solution, right? So this is a bit strange. Now, generally speaking, the metals tend to form alkaline solutions. So we're looking at a non-metal. Now, let's think of the non-metals. Nitrogen won't react with water, so it can't be that. Oxygen doesn't react with water; it just dissolves. Sulfur, phosphorus, and sulfur don't. Chlorine will react with water. As you know, chlorine disproportionates in water, so you get H2O plus Cl2, gives you 8Cl, which will make it acidic, and also HClO, which is a weak acid, but that will also make it acidic. So chlorine is the answer there. I think you probably also could have fluorine there. Fluorine is going to react with water, and it makes HF, which is acidic, but I'd go for chlorine there because we're more familiar with that. Okay, an element which forms a compound with hydrogen, XH3. Now, so which group is that coming from? It is probably group 5. If you think nitrogen forms NH3, doesn't it? Ammonia. But the MR of NH3 is only 14. So it's got to be phosphorus then. Okay, phosphorus is 15. So pH, phosphorus is 31, sorry. pH 3, 31 plus 3, 34. The answer is phosphorus. An element for this one here. So an element that reacts, which forms a compound with hydrogen, in which the element has an oxidation number of -4. Hydrogen always has an oxidation number of +1, doesn't it? Nearly always anyway. So that means you're going to have XH4, 4 hydrogens, and straight away methane would be, so CH4 would be the one that I would choose. You could also have silane, silicon, SiH4, but methane is more obvious. Okay. Right, the element which has the density of this, right, well, it's got to be a gas, hasn't it? Okay, if it's that light. Right, we're going to use the fact that 1 mole occupies 24,000 centimeters cubed, doesn't it? At room temperature and pressure. So 1 centimeter cubed has got a mass of that. So mass of 24,000 centimeters cubed, i.e. 1 mole of that gas, is 1.33 times by 24,000. And if you do that, I think it comes out at just under 32. Okay, so the MR of the molecule is 32, and that, well, what could that be? It could be oxygen. Okay, with oxygen 16, that's what it is. Okay, right. Period 3 chlorides. Explain the properties in table 1 in terms of bonding and structure. Okay, so what we're going to say, NaCl, it conducts, it's got a high melting point. Why? Because it's an ionic solid. You've got strong electrostatic attractions between sodium ions and chloride ions, we'd say. And it is a good conductor because when molten, because the ions can move. You could use the same arguments for magnesium chloride. Again, it's an ionic solid, so high melting point, and it will conduct when it is high melting point, strong attraction between Mg2 plus ions and chloride ions, electrostatic attraction, and it will conduct when molten because the ions can move. SiCl4, well, that is that's a small covalent molecule. So why has it got a low melting point? Is because you've only got weak intermolecular forces. You're going to have London forces between molecules, between silicon SiCl4 molecules. There's no permanent dipole in SiCl4 because it is symmetrical. You're only going to get London forces. And it won't conduct electricity because there's no delocalized electrons and no ions. Okay. PCl3, again, that is going to be a simple molecule, simple covalent. We'll have a dipole because it's not symmetrical, so you're going to get dipole-dipole interactions between PCl3 molecules, but they're not very strong, and so it's going to have a low melting point. And it won't conduct because it's got no delocalized electrons and no ions. SCl2, well, that's a simple covalent molecule again. We'll have a dipole, so you're going to get dipole-dipole interactions, same as PCl5. Won't conduct, no delocalized electrons, no ions. Okay. Right. Reaction of hydrogen peroxide and of cobalt-2 ions. Okay. Aqueous hydrogen peroxide decomposes according to this equation to give water and oxygen, and it's catalyzed by manganese dioxide. Okay, so a student investigates decomposition. He puts in 50 centimeters cubed of hydrogen peroxide solution, adds some catalyst, and quickly connects and measures the volume of the oxygen gas every 20 seconds. You see, you're going to have to plot a graph here, which I've done already, and it's in the next part of the question. So there's the results, there's the time, and there's the volume of oxygen produced with time. Okay, now let's see what the question says. Okay, it says, process the results as outlined below. Plot a graph of volume of oxygen against time and use your graph to find out the rate of reaction at that point. Okay, right, so we're going to do that. So I plotted my results, the results, blue crosses and this green line, and you can see the gradient of the green line. Okay, so we put the volume of volume of oxygen on the y and time on the x-axis. Okay, so it's a curve. The gradient gets less, the reaction is slowing down because the concentration of the hydrogen peroxide decreases. And we've got to find the rate at 500 seconds, it says. So what we need to do is draw a tangent to the line at 500, which is there. So that green line, that yellow line is the tangent I've drawn. And now we need to find the gradient of that tangent. So what I'm going to do is right here, we have got, sorry, let's do the change in y first. So gradient m is equal to the change in y over the change in x. Let's do the change in y, which is that green there. So that's going to be 50 minus, that is 14, which is equal to, that's going to be 50 minus 14, that is 36 centimeters cubed. And how long did that take to happen? Well, here is our change in x up here. So that there is, right, that is 875 there minus 0. So that's delta x is equal to 875 seconds. So we need to do that, and that's going to give us 36 divided by 875 is 0.0411, and the units, well, that's in centimeters cubed and that's in seconds, so it's centimeters cubed of oxygen per second. There's our answer there. Okay. All right, let's carry on with this question. So that's that bit done. Right, now the student allows the reaction to proceed until no more gas is evolved, and he has 55 centimeters cubed of oxygen in the syringe at that point. Right, just to remember, that came from 50 centimeters cubed of hydrogen peroxide solution. It told us that earlier on in the question. Calculate the initial concentration of H2O2. Right, so we need the equation here as well. 2H2O goes to 2 hydrogen peroxide goes to 2 H2O and 1 oxygen. Okay, so let's find our moles oxygen. Right, that is equal to the volume in centimeters cubed divided by the volume of 1 mole, which is 24,000. So that's 55 over 24,000, which is equal to 2.29 times 10 to the minus 3. So now we can see here that 2 moles of hydrogen peroxide only give 1 mole of oxygen. So therefore we have to double that. So moles of hydrogen peroxide is equal to 2.29 times 10 to the minus 3 multiplied by 2, which gives us 4.58 times 10 to the minus 3. Okay, now that's how many moles of hydrogen peroxide we had, and it came from this volume, 50 centimeters cubed. So concentration is equal to moles over volume, equal to 4.58 times 10 to the minus 3 divided by the volume, which is 50 over 1,000 dm cubed, and that gives us a value of 0.0916 moles per decimeter cubed. It tells us to give our answer to 2 sig figs, so that's going to be 0.092. That is the concentration of our hydrogen peroxide solution. Okay. Now here we've got cobalt. Okay. Cobalt forms complex ions with water ligands. All right. So in water we have this pink complex here, and it forms a blue tetrahedral complex with chloride ligands. All right. So I'll just draw the formula of the chloride. So the when you've got chloride ligands, you get 4 tetrahedral. Remember, the chloride ligands are too big to fit 6 around. That's why you only get 4. And the charge on that's going to be 2 minus, because the cobalt's 2 plus, and each chloride is -1. There's 4 of them. So that's the blue species that we've got. So what he did was he got the put the boiling tube in a water bath, and he added concentrated hydrochloric acid until the pink turned blue. So what is happening there, we're getting a ligand exchange reaction. I'm going to write it down here. So we're going to get CuH2O6 2 plus, and we're going to need 4 chloride ligands there to push them out. An equilibrium reaction, and we're going to get the blue complex, the CuCl4 2 minus, and we will also get 6 water molecules coming off here. Okay, that, and you're going to ask for that equilibrium reaction afterwards. So that is pink, and sorry, 2 minus there. The red one's pink and the blue one is blue. Okay, so he does that. It's at 100 degrees C, and then they put it into cold water. Okay, so at 100 degrees C, it's gone blue. When you put it in cold water, it goes back to pink. So what we're going to say there is, when it's in cold, the equilibrium shifts to the left. Okay, right. So we'll answer this question first. Write the equilibrium reaction. That's just that one there. The next question is, explain the observations and predict whether the formation of the blue color is exo or endothermic. Well, we know when we've got this equilibrium, okay, when we make it colder, it goes backwards, right? If we make it colder, it will move in the exo direction. So we know backwards it is exo, so that means forwards it must be endothermic. So the formation of the blue color then is endothermic. It's kind of Le Chatelier's principle. Okay, right. Right, now it's a question: ethane dioic acid and ethane dioate ions. The ethane dioic acid is a bidentate ligand, so the lone pairs on these oxygens can form the coordinate bond to the central metal ion, which in this case we're told is Fe3 plus. Right, now it's draw the 3D shapes. The complex ion has 2 optical isomers. Now the reason for this, you should know, is that when you've got a bidentate ligand, right, this is going to, the Fe3 plus is going to have a coordination number of 6. It's going to form an octahedral complex. So we've got to draw the shape of the optical isomers. So I'm going to draw one of them first. I'm going to draw Fe. Now it's octahedral, so you're going to have 4 of the ligands are going to be in the same plane of the paper. And we're going to have 1 is going to be coming out to you, and then 1 is going to be coming back into the paper there. So that's what the ligands are, and they are going to be this ethane dioate ion. So I'm going to draw them here. So we've got those oxygens are forming, okay, and we've got the carbonyls here. And then we're going to have another one, which is going to use in this position here. And finally, we're going to have another one here. Now, we need to draw the optical isomer of that, so we need to draw the mirror image of it. So I'm going to draw that here. So I'm going to draw my imaginary mirror here. The Fe, there's 4 in the same plane. Now this, because this is a mirror image of that, the one going backwards is going this way, and this one, the wedge one coming out of the paper, is there. And right, I'm going to put mirror image. I need one, should be blue, do it in blue. We're going to have one here, and we're going to have another one up here. And finally, this one on the other mirror is going to be over here. The mirror image of it is here. Right, it does say here, show the structure of the Ethane dioate ligands. We've done that. We've shown skeletal formulae and any overall charge. So each ligand has got a charge of 2 minus, and there's 3 of them. So that's equal to 6 minus, and the Fe is obviously 3 plus. So that means the overall charge on this species is going to be 3 minus, and the same on the other isomer as well. Okay, so that is the special case when you get bidentate ligands which form octahedral complexes. They exist as 2 non-superimposable mirror images to optical isomers. Okay. All right, more about ethane dioic acid here, and they've represented the formula like that. Okay, it's present in rhubarb leaves, and this is a titration. Right, so he uses cerium, the student uses cerium 4 sulfate to determine the mass of ethane dioic acid in rhubarb leaves. So this is the reaction. Cerium 4 plus will oxidize the succinic, the ethane dioic acid, to carbon dioxide, and that will be reduced in the process to the 3 plus ion. Right, so he weighs out that mass of rhubarb leaves, extracts the ethane dioate acid, makes up a solution of ethane dioate to 250, and he's only taking 25 out of this time each time for titration. So it's the usual thing where you take 1/10 of the solution out for titration. Now, before we can do that, the student does repeat. So we have to work out the titers. So I've done that already by subtracting the initial from the final. Which 2 are concordant? It's the 2 I've underlined here, that one and that one. And so the average titer is 23.2. Right? It asks you to do that. And then next. So we need this value later on. Okay. So what we've got to do is calculate the percentage biomass of the ethane dioic acid in the rhubarb leaves and give it to. Okay, so how are we going to do it? So what I've done is I've copied the instructions, or what the student did again. So let's go through this. Okay, so what he's got his rhubarb leaves, those green things there, 82.68 grams of rhubarb leaves. He extracts it just to get the ethane dioate, which I've written like that. That's made up into 250 solution. Take 25 out, and you titrate against this yellow cerium ion. Okay, and the endpoint is going to be right. So the 4 plus ions are yellow, and these 3 plus ions are colorless. So the endpoint, as this yellow stuff goes in, its color is going to disappear as it turns to Ce2 plus until you get to the endpoint, and then the yellow color will persist in that bottom there. So you're looking for the first permanent yellow tinge there. Okay, so we've got to work that out. Right, so right, let's work out our moles of Ce4 plus first of all. So moles of Ce4 plus in the titer is equal to the concentration times by the volume. Well, the concentration of the Ce4 plus, they tell us, was right. It was 0.05. So 0.05 moles per decimeter cubed, multiplied by the average titer, which was 23.2 centimeters cubed over 1,000. there's a volume in dm cubed. So that gives us a number of moles of cerium 4 plus of 1.16 times 10 to the minus 3. Okay, so the moles of the, now we have to do the moles of the ethane dioate. Well, we look at the equation they've given us, and 1 mole of ethane dioate reacts with 2 moles of cerium, so we've got to halve that. Okay, so the moles of that is equal to 1.16 times 10 to the minus 3 divided by 2, which is equal to 5.8 times 10 to the minus 4 moles. That's in 25 centimeters cubed here, but the total amount we had up here was 250, so therefore we're going to do the moles in 250. So moles of the ethane dioate in 250 is equal to, times that by 10, 5.8 times 10 to the minus 3. Okay, so we need to work out a mass of that now. So the mass is going to be that multiplied by the MR, moles times by the MR. The MR of this is 90. So the mass is going to be 5.8 times 10 to the minus 3 multiplied by 90, which is equal to, how many grams is that? 0.522 grams. Okay, so we've got 0.522 grams. Now it wants us, that came from a total mass of 82.6 grams of rhubarb leaves. So the percentage is going to be of rhubarb leaf, which is ethane dioate, is the mass of ethane dioate divided by the mass of the leaves times 100, and that it gives us a value of 0.631. Okay, appropriate number of significant figures. Well, everything is given to 3 sig figs in that question. Well, actually, some things are given to 4, but that's given to 4 as well, isn't it? Okay. So yeah, we should give it to 4 significant figures then. So whatever that is to 4 significant figures. Actually, no, that is only given to 3 significant figures, that one. So we'll leave it at 3 significant figures. 3 significant figures is the right degree of accuracy. The least accurate piece of data, that's what you should quote your final answer to. Right. This is about cisplatin. Okay, so this is this compound anti-cancer drug. Okay, what's the oxidation number of platinum in cisplatin? Well, the NH3 ligands have no charge. The chloride ligands have a charge of -1, and the overall complex is 0. So that means the platinum must have a charge of 2+ in the complex. So the oxidation number is +2. Right. Cisplatin is prepared in a ligand substitution reaction, which takes multiple steps. The equation for the final step is, so you've got 3 chlorines and you're going to replace one of them with an ammonia ligand. In the box, outline the mechanism for the formation of cisplatin. Okay, so what we're going to do is this one, the starting material is PT, and we've got, we've actually got 3 chloride ligands. Let's draw them. And 1 ammonia ligand. There's a chloride. Now the ammonia is going to come along, and the lone pair on the ammonia is going to form a dated bond to the platinum, like that, curly arrow to the platinum, and that means this ligand is going to break the dated bond, so that pair of electrons goes onto the chlorine to give us the chloride. So there is our mechanism. Okay, moves on to paracetamol now. Okay, paracetamol, there's the structure. Name the functional groups present in paracetamol. So we have got this, which is a phenol functional group. And here we've got a nitrogen next to a carbonyl, and there's an alkyl group on the carbonyl. So, sorry, it's not relevant. You've got a nitrogen next to a carbonyl, but because we've got this, we haven't got, it's not an amide, it's actually a secondary amide, isn't it? Because you've got another carbon there, which is attached to the nitrogen. So a secondary amide is the answer there. Right. Preparation of paracetamol from 4-nitrophenol. Okay. Describe a two-stage synthesis. The overall percentage is that. In your answer, include the mass of nitrophenol, the reagents, and the intermediate. Okay, so what intermediate are we going to get? Right. What we've got to do first of all is we've got to reduce that nitro group to an NH2 group, so that can then react with the acyl chloride. Okay, so the intermediate is going to be where we've got an NH2 on the benzene ring now, and then that's going to react with the acyl chloride. So that's our intermediate. What conditions do we need to reduce? We've got to reduce this to that. It's a one-off, that one, isn't it? It's we need the reducing agent is tin, and it's got to be present in conc HCl as well. So that are the conditions and the reagents. Right, now we've got to do the calculation to find out, include the mass of 4-nitrophenol we need to start off with. Okay, so it's a percentage yield calculation, so we need to work out the MRs, molecular masses of 4-nitrophenol and paracetamol. So I'm going to do it. So that bit there, that's C6H5 O would be the molecular formula of that bit, and that's 95. And then we've got to add on NO2, that's 46. So the MR of that thing is going to be 139. Okay, of the starting material. And what's the MR of paracetamol? Well, once again, we've got this bit here, which we said before weighs 95. And then we've got 14 plus 1, 15 plus 12 plus 16 and plus 15 for that. That all adds up to 58. So the MR of the paracetamol, 58 plus 93, 151. Okay, that's the paracetamol. Now we want to make 5 grams of paracetamol. So how many moles of paracetamol is that? Is equal to mass over MR. 5 over 151, that gives us 0.0331 moles. 1 mole of paracetamol. Well, so 1 mole of 4-nitrophenol gives 1 mole of paracetamol. Okay, so the number of moles of 4-nitrophenol we need is the same. So I'm going to do the mass of nitrophenol we need now. We're presuming 100% yield at the moment, then we'll do the 40% bit afterwards. So the mass of nitrophenol is going to be moles times MR. So that's 0.331 multiplied by the MR of that was 139. That is equal to 4.6026 grams. Now that is if you get a 100% yield, but we don't. We only get a 40% yield, okay? So for if 100% yield, we need 4.6026 grams. So let's say if we get a 1% yield, we would need 100 times that. So we would need 46.26 grams. But we don't get a 1% yield, we get a 40% yield, so we only need a 40th of that. We need 460.26 over 40, which is equal to 11.5 grams. That's how much we need. Okay. So that's that question finished. Right, now on to one about forming an ester, and okay. Oh no, delta H, this one, sorry, it's a neutralization first of all. Right, this reaction we can use to determine a value for the enthalpy of neutralization, okay, of this compound. Right, so what we're going to do here is we are going to use Q is equal to MC delta T. That will give us the heat, Q quantity of heat released in our experiment. And what we need to do then is convert that into delta H, which is equal to Q divided by, now because it's neutralization, we should really work out, and we form it's per mole of water, okay? So mole H2O formed. So we've got to use that equation first, that one there, and then we've got to put it into this one to do that. So let's do that, shall we? Okay, so Q, right, is equal to the mass of the solution. So we've got 50 and 50. So that's a total of 100. Okay, so that's going to be 100. Right, and the specific heat capacity of water, C, is 4.18 joules per gram per Kelvin. And the temperature rise, well, 26 minus 21, 26.5 minus, so that's delta T is 5 degrees C. So that's times 5. Work that out. That gives us a value of Q of 2090 joules. Now we need to work out delta H, but we need to work out the moles of water formed. Okay, so it says here we have got, right, we've got excess NaOH. Okay, so we're not going to work out the moles of that. There's too much of that. Not all of that is going to react. I'm going to work out the moles of succinic acid. Okay, how many moles of succinic acid have we got? Is equal to the conc times the volume. The concentration is 0.4 and the volume is 50 over 1,000 centimeters dm cubed. Convert that to dm cubed. That gives us 0.02 moles of succinic acid. But we need to find out the moles of water there. Okay, so look, every time we use up 1 mole of succinic, we make 2 moles of water. So therefore the moles of H2O formed is equal to 0.02 times 2 is equal to 0.04. So now we've got to put it into this equation. Okay, so we've got delta H is equal to Q, which was 2090, divided by the number of moles of water formed, which is 0.04. Do that, that gives us an answer of, right, 52,300 joules. So I'm going to convert that into kilojoules. And then I'm going to have to remember, of course, that this is, the temperature has gone up. It's an exothermic reaction, so don't forget to put minus in there. I think if you don't, you'll lose a mark. Okay, so that is the enthalpy delta H neutralization. We've worked it out there. Minus 52.3 kilojoules per mole of water. Okay, I think this is the final calculation. Okay, succinic acid is esterified with ethanol in the presence of an acid catalyst. Okay, so if you think how that is going to work, well, succinic acid is butane dioic acid. So you have got that there. And you're going to esterify it on each end with ethanol. So if I just draw ethanol at that end, we're going to have in red. Just do C2H5 there, and the same at this end. Right, and so what's going to happen is we're going to form that. I should really do, actually that oxygen comes from the alcohol, so I'm going to put it in red. We're going to do that. That's the ester we're forming there, which is that thing. That's how they've written it there. Okay. Right. Okay. So that is the equilibrium expression. Okay. And they have done it in amounts of moles, which of course we don't normally do. We normally do it in concentrations, don't we? So normally we would have like the concentration of water, not the number of moles of water squared. Yeah. Okay, but it's okay to do that, and they ask us why. Okay, in a minute we'll talk about it. Why? Right. What technique? So student carries out an experiment to determine Kc. So he mixes some succinic acid, mixes it with the ethanol, added a bit of acid catalyst, lets it reach equilibrium, leaves it, and at equilibrium he finds out you form that much succinic. Well, that much succinic acid is left over, so we should be able to work out the moles of ester and stuff. What technique could you use to determine the equilibrium amount of succinic acid? Well, it's an acid, so we could titrate against sodium hydroxide. Write the equation for the equilibrium reaction that takes place. Okay, right. So that is going to be, right, I'm going to write it down like this. There's my succinic acid plus 2 ethanols. So I've swapped over colors, so I'm going to call that. I'm going to write it down like that, and that is going to go to form the ester, which is going to be CH2, CH2, COO, and then we've got our other ethanol there, CH2, CH3, plus water. We're going to have 2 waters formed, so we get a water for each ester linkage formed. That's the equation there. It's too long to draw it on one line. I've drawn it on 2 lines. Right, draw the skeletal formula for the ester present in the equilibrium mixture. Okay, so we've got our butanoic acid. I'll draw that in red, I think. Okay, so we've got 2 carbons, 1, 2, and then we've got a carboxylic acid on that end there. So let's just number these carbons. Be careful. Like 1, 2, 3. There's the 4th carbon. There's the carbonyl group on that, and then we've got our ethyl groups, the esters, stuck on here. So we need an oxygen first of all, don't we? We need an O, and then we want that's 1 carbon of the ethanol. That's the other carbon of the ethanol, and the same on this side. 1 carbon of the ethanol, 2 carbons of the ethanol, and there's our carbons for the it's butane dioic acid, succinic acid. This is 1, 2, 3. We've got 4 carbons there. So that's our skeletal formula. Right now, right, okay. Well, I've done that. Sorry, that's repeat stuck in twice for some reason. Right, and then, right, Kc is the equilibrium constant in terms of the equilibrium. Kc is the equilibrium constant in terms of equilibrium concentrations. Why can expression 4.1, 5.1 be used in this case? Well, the reason why is if you look at this, if you look at the equation here, you have got the same number of moles on both sides of the equation. On the left-hand side of the equation, we've got 1 and we've got 2, got 3 moles, and on the left we've got 1 of the ester and 2 waters. So we've got the same number of moles on both sides of the equation. Now, whenever you have that, the volume terms will cancel out, okay, because you've got 3 lots of volume on the top, okay, and 3 lots of volume on the bottom, so they will cancel out. It's only 1 mark, so all you have to say is you've got the same number of moles on both sides of the equation. But you know, just so that if you're wondering, Kc should really be, I'm going to write down the concentration of ester multiplied by the concentration of H2O squared divided by the concentration of the acid multiplied by the concentration of the ethanol squared. So you can replace those concentrations with moles like they've done. So ester, that's the moles of ester, over V, multiplied by the moles of water over V, the acid, so that's all squared, acid over V, multiplied by the ethanol over V, all squared. So if you multiply out those brackets, you're going to get H2O squared over V squared and ethanol squared over V squared. And you can see you're going to have 3 terms of V on the top line and 3 terms of V on the bottom. So all those V's all cancel out. So you don't actually need concentrations. You just need the number of moles. You don't have to say all that. As I say, it's 1 mark. Just say same number of moles on both sides of the equation. Now we've got to calculate Kc. So I've done one of these start moles, used up moles, equilibrium moles diagram as usual. Okay, so there is our equation, and I've written down, I've copied in the instructions again. So it says, let's see what happens. Student starts off with 0.05 moles of succinic acid. Okay, so we start with 0.05 of that. And 0.15 moles of ethanol, and we haven't got any of that and no water. Now, at equilibrium, you've got 0.02 of succinic left over. We've got 0.02 moles left over. So that means we've got, how much have we used up of that? 0.05 minus 0.02 is equal to 0.03. Now, if you've used up that much of succinic, we've used up, sorry, there should be a 2 there. We've used up double that of ethanol. So it's going to be 2 times 0.03, which is equal to 0.06 of ethanol. And we're going to subtract 0.15 minus 0.06. So we have 0.09 moles of ethanol at equilibrium. Right. Now let's see here. We have used up 0.03 of the acid, so that means we're going to make the same amount of the ester there, and we're going to form double that for water, because we form 2 moles of water. That's 0.06 for that. Okay, so we need to put that into our Kc expression, which we've pasted down there. So Kc is going to be equal to the moles of the ester, which is 0.03, multiplied by the moles of the water squared, 0.06 squared, divided by the moles of the succinic acid, 0.02, multiplied by the moles of ethanol squared, 0.09 squared. Put all that in, what do you get? 0.667, and there's going to be no units because you've got the same number of moles on both sides of the equation, so all the units will cancel out. That is that one there. Okay, now Right, this is about organic reactions. This is quite a tricky question. Okay, right, give the systematic compound for name for compound A. Well, we have got how many carbon atoms here? We've got 1, 2, 3, 4. So it's going to be, and then we've got an aldehyde group here, so it's going to be butanal. But we've also got an OH on carbon number 3, so it's 3-hydroxy butanal. Now, I would call it 3-hydroxybutanol, but I looked in the mark scheme and they insist, for some reason there, they want 3-hydroxy butan 1-al. Right, I'm not entirely sure why they want that one there, but they do. Okay. Right, what kind of reaction has taken place there? That is quite tricky. Okay, so let's see what's happened there. Now, we have got, let's look at these I'm going to draw these hydrogens here in red. Well, the aldehyde, that has remained untouched. Okay, so that's nothing happened to that. But these hydrogens, that's where the red hydrogens have come from. So what has happened is that hydrogen has gone, and that carbon has attacked that carbon because it will have a negative charge. You lose a proton, and then that's going to go in there. Well, what kind of reaction is that? You probably recognize it as being a nucleophilic addition reaction. It asks us about the mechanism later, but what happens is, if I just make this a bit clearer, is this second, okay, so this ethanol molecule, what's going to happen is it's going to lose a hydrogen. Okay, now it loses the hydrogen because you mix it with a strong base, OH minus. So that's removed. This hydrogen, that one I've just drawn there, that gets removed, but it leaves its electrons behind. It gets removed as an H plus ion. So you've got a negative charge on that carbon. You've got a lone pair, and this is the nucleophile that then attacks that carbon. Okay, so let's answer the questions there. Step 1, ethanol reacts with OH minus to set up an acid-base equilibrium. In step 2, a compound A is formed. Complete the equilibrium for step 1 and label the acid-base conjugate pairs. Okay, so you're going to form this thing here, which is CH2, CHO, and that's got a minus on there, and you're going to form water. Right, so this is behaving as a base, so let's call that base 1, and this will be its conjugate acid, that's acid 1. When it goes backwards, the water is given away an H+. This has behaved as an acid because it's lost a proton, and this would be its conjugate base, so that's A2, and that is going to be base 2. Suggest the equation for step 2. Step 2, compound A is formed. Right, so I've kind of shown the mechanism of that. So what we're going to get there is the equation is going to be CH3 CHO plus CH2 CHO. That's going to be a minus. I'm going to put a proton in there as well. And the final thing, the final compound, has got a formula of CH3 CHOH CH2 and the intact, that aldehyde, yeah, and the intact aldehyde on the end there. Should really put a bracket around that, maybe just to make it clearer. That's an OH. And if you check all the hydrogens there, that's completely balanced. Okay, that's what happens in step 2. Right, a similar reaction takes place when propanone mixes with OH minus ions. Draw the structure of the organic product of the reaction. Right, so I'm going to draw propanone here. I'm going to draw that as CH3, and I'm going to draw this one as like that. Right, so we're going to lose a proton off there. So that's going to be a minus, isn't it, there? And let's draw a different color propanone here. What's going to happen is that pair of electrons is going to form a new bond, carbon-carbon bond to that, and then that pair of electrons is going to go in the oxygen. That's going to pick up a proton. So the final thing is going to look like this. That ketone is intact. We've got CH2, and that is attached to this green carbon here, and that green carbon has got one CH3 there, another CH3 there, and it's going to have an O minus, which will pick up a proton to become OH. So that is the formula of the product with propanone. Okay, now finally, the very last question is a question about a 6 marker, the role of electrophiles as reagents. Right, explain the role of electrophiles. Your answer should include one reaction of an aliphatic compound and one of an aromatic, including relevant mechanisms. Okay, so that is fairly reasonably straightforward. It's right. First of all, I think we need to say what an electrophile is. Species which accepts a lone pair of electrons. It's electron deficient. It's going to accept a lone pair of electrons. Right, let's do this one, an aliphatic compound. Okay, now that means really this is electrophilic addition. And that is going to be with, let's choose ethene, which is about the simplest thing we can have. And that is going to undergo an electrophilic addition reaction with something like HBr. This HBr is okay. So we are going to have a partial positive charge on the hydrogen here because the bromine is more electronegative. And remember this reaction, if you remember this, the first thing is the pi bond breaks. So the pair of electrons of the pi bond go onto the hydrogen to form a new bond to it. And then that bond has got to break, the bromine ends up with the electrons there. Right, we get an intermediate there. We've got that's the new hydrogen stuck on. And we have got a positive charge on that carbon. It's a carbocation. And we've got a bromide ion left over. Right, and then that bromide ion is going to react with the carbocation to form bromoethane. So that is electrophilic addition, and that is our one with an aliphatic compound. Now you may remember the electrophilic mechanism with an aromatic compound is actually electrophilic substitution. Okay, so let's do that. Electrophilic substitution, right, because you don't want to break the delocalized system of the electrons. So here's our benzene, and we need an electrophile. So the most obvious one to use, I suppose, would be the NO2 electrophile, which has been generated with conc nitric and conc sulfuric. We don't need to talk about that. The question's not asking about that. Now, the first step in the mechanism is the pair of electrons, one pair of electrons, and the delocalized system jumps onto the nitrogen. That is then going to form this. Right, so I'm going to stick the NO2 onto there. That goes to the N, that bond. And we usually show the fact there's a hydrogen there. There's a hydrogen on every carbon, but just to remind us. And the delocalized system has been partly broken. So we draw that like this. And of course, that's going to have a positive charge, and that's spread over the whole benzene ring. And the final step in the mechanism is for the delocalized system to reform. So a pair of electrons comes out of this bond, back into the ring, and we get our nitrobenzene, and we get an H+ ion as well. So that's electrophilic substitution. So that was our reaction with the aromatic compound. I would have thought there's well enough points in that answer for 6 marks. You don't need to add anything else there. That's it. Okay, and that was the last question in the paper.